first electrode hits the scrap, on scrap, yeah? And now the second electrode is hitting the scrap. Can there flow a current?
Yeah.
They can? Over this?
Yes.
This loop
Yeah.
is giving the current, yeah? Where is the star point moving? This is the active voltage who gives a short circuit over these two electrons. And the point of this may be between 1 and 2, maybe here. When 1 und 2 on scrap. Yeah? And this is the first voltage. 1, 0. And this is the second voltage. 2, 0. Yeah? And the voltages, this is small because we have nearly a short circuit. The voltages are inductive, the currents are inductive currents. You have an inductive current. We have this. Yeah? And here an inductive current like this. And the sum of these two currents is 0. This plus this is 0. Okay. And you have here, most of the voltages are inductive. Okay, this is the voltage, this is the current, this is an active voltage, and this is the inductive voltage, Ux. Yeah? 1 and Q1. Therefore, I show this, and this is the voltage to phase 3. 3, 0. You have a big ignition voltage. This is very good. Forget the third ignition. These are moving high, and you get by the control, you get an arc, and then during furnace operation should be so. What I want to say to you, that this star point is moving in this triangle. It's not free. And if you have unsymmetrical system, the star point is not here, maybe here or here or here. If x1 is not identical with x2 and x3, the star point is outside the middle. Is that clear, buddy? Yeah? Maybe the star point is here. Yeah? And this is the first, second, and the third. And therefore we do not know how much is this voltage, and we do not know how much is this. This is the voltage, and we do not know how much is this voltage. Therefore it's not easy to calculate the currents. Not easy. Because you cannot say this is the same voltage than before. The voltage is varying. And during furnace operation, the star point may move in this area. This is this is what you need, and if you want to make a calculation, I've tried this. You want to make a calculation. You see, this is, I will not calculate this together. We have three equations. 1, 2 is the 1, 2 is the voltage drop at the resistance plus minus the voltage drop given by the current 2 this is the voltage, phase voltage 1 to 3. You can get the second deviation E2 R2 plus X2 minus E3 R3 plus X3, and we need three equations for three currents, 1, 2, 3, and we need a third equation, and the third equation is that the sum of the currents is 0. There's no earth conductor. There's no earth conductor. Please, this is not possible. We do not have an earth conductor. There's no bottom electron in the AC furnace. In the DC furnace you need a bottom electron, but not here. This is an advantage. And with these three equations you can calculate the three currents. I have calculated the current E3 and this is not a good equation. You can also write the formula for phase 2 and 1. But to work in the steel plant with these equations is not good. It's not good. This is the reason, one of the reasons also for the man who is working with the impedance control. He must know how the impedance of the system shall be, and you will also, if you have an unsymmetrical system, X1 ungleich X2 ungleich X3. You see, all currents and all powers are not symmetrical. And it may be that in one phase you have too much power and you have destroying the wall. We say this is the hot phase. And in the other, we have not enough power. This is a cold phase, hot and cold phase. And there's another disadvantage is you cannot reach the maximum power. The power you get is smaller than this power. And this is the reason why it is not good to work with a furnace with unsymmetrical system. I'm telling this because all of the design of these systems have the idea what can I do to make a symmetrical reactance system. This is the reason. Is that clear?
Yeah.
It's okay? Okay, number 2. Okay. Well, this is my first step. Reactance is an important parameter of the furnace power. I must now speak about short circuits and operational reactance. During furnace operation, the reactance seems to be higher. Yeah? And if you make a calculation of the system and you forget this will not good for you. You get a little bit trouble. Maybe that has locked somebody. Hat seinen Koffer vergessen. Sie haben Ihren Koffer vergessen? Da vorne? Ach so.
Ja, nee, den hat er.
Ach so.
Nee. Was ist denn der?
Nee.
Diese.
You see this is an electric arc furnace from 1920, 7 tons. These are not water cooled. Yeah, this is air cooled. You see, but the construction is the same than today. 3 electrodes and triangle, and so they started 100 years ago. Yeah, these are all cable, not water cooled cable. But the construction, the idea is the same, and they are parallel. Yeah, they are parallel. Alice said the equation in the middle is good if you have a loop. If this is a loop. Yeah? Okay. Now I would like to looking for a paper which says you know what a circle diagram is? Professor Krüger spoke to you. This is a circle diagram. This shows the active power against the reactive power. If you make with this construction a circle diagram and you visit the furnace operation, then you see that all points during furnace operation are not identical with this. And you may think about what is the reason that I cannot get working points on this ideal circle. The reason is we have harmonics in the current. Harmonics. Yeah. We have not constant flowing current. The current is changing its amplitude. And we have unsymmetrical currents. And we have also additional impedances of the furnace transformer, of the supply network, and these increase the reactance. Therefore, we must speak about the operating reactors during furnace operation. On these, there are some models to calculate, if you calculate the current, and one of is given by Mr. Köhle. He says there's an additional arc reactance which can be given to the arc, and this is dependent from the arc resistance. The higher the arc resistance, the higher the additional arc reactance. Okay? There are many years. Außerdem, he also said that these additional arc reactance, this is the additional, this is the arc, is time changing with the time. During boring period, this is much higher in comparison to forming slack operation. This is very small at the end. And then Mr. Bowman, you know Mr. Bowman from Union Carbide, he has made many measurements and asked how is the additional increase of the reactance, the ratio between the operating to the short circuit reactance during furnace operation and during the working point. This is a cosinus of the phasing. This is long arc, this is short circuit. And he said, if we start boring, it can be 50% higher. If we are boring with cosinus phi, it's 0.8, and during main melting, it is going down, and if we are forming slack, is only 10%. This is clear for you, if you have seen a furnace operation. What is, you see, this is the time dependency of the arc reactance given by Mr. Köhle, and you can also make experiences. This is the furnace power of the Hamburg steel plant. I have made this. This is the power of the furnace dependent from the current of the furnace. You see, this is the power diagram if we have no operation reactance, which the factor is 1.0. You see that in the ideal construction, the furnace makes 100 megawatt.
Yes, that's correct.
100 megawatt. But if you start boring period, the furnace is only less than 80 megawatt. Because the additional reactance from the furnace operation is high. And if you go in the main melting period, it's increasing more than 80 megawatt. And if we are forming slack operation, the power is increased to more than 90, more than 90 megawatt. This is the influence of the operation of the operating reactance of the furnace power. Is that clear? This is what you must know. If you make a construction of a high current system, you must know this. Yeah? You must know this. Please, it's dependent if... Ja, Sie wollen nach Hause gehen?
Ja, wenn Sie,
Okay.
wenn Sie mich nicht mehr brauchen, ich bin noch
Nein? Okay. We thank you all for your kind explanation, and he is also for you. If you have more questions, please send him a mail. Yeah, you can do that.
If I can ask by telephone until Friday morning, I will do it.
Yeah, until Friday morning we can speak together by phone. I will do it if necessary. Okay? Okay?
Okay. Bye bye. Thank you very much. Tschüss.
Vielen Dank. Ja,
Thank you very much.
kommen Sie gut nach Hause?
Ja.
Kommen Sie gut mit Ihrem Auto raus?
Ja, du musst eben noch eine Ersatzkarte für den Parkplatz, denn die war weg jetzt.
Aber ich glaube,